Hey, welcome back AP Calculus students. Today we're looking at accumulation and net change 8.1. So we're going to be talking about the relationship between position, velocity, and acceleration again. So remember that if we do the derivative of position, then we get to our velocity, and if we do the velocity's derivative, then we get to our acceleration. Now, the same is also true if we integrate. So the integral of a gives us our velocity, and the same thing with the integral of v, it gives us our position. So they undo each other. So as we work down the chain with derivatives, you can work back up the chain by using integrals. All right, so we have this equation here. So it's saying the ds dt is representative of the velocity of t, and that's also equal to t squared minus 8 divided by the quantity t plus 1 squared. So it says describe the motion from 0 to 5. Now what we're going to do here is we're just going to go and put this into our calculator in Desmos. Whoops, that's not it. Okay, so we're going to put our function in, we'll do x squared minus 8 divided by x plus 1 squared, and we're going to graph it. So notice when we're talking about the velocity function, we're always interested in where it's 0. So it's 0 here, right, at 0.1225. Okay, and because we're talking about velocity, anytime our velocity is positive, so to the right side of that point, it's positive, it's moving to the right. Anytime our velocity is negative, it's moving back to the left. So when it's asking us to describe our motion, we can say pretty easily that, oops, that's not the right one. It comes to rest at 1.225 seconds. From 0 to 1.225 seconds, it's moving. Remember, it was negative, right? It was below the x-axis on that side. It was moving to the left. And then from 1.225 to 5, right, because that's the end, it's moving to the right. Okay, so pretty easy when we do the graph of it. If we try to do it by hand algebraically, it wouldn't be as easy because it's not a quadratic. We're going to have a t to the 4th eventually, which is not as easy to solve for. Okay, example 2. From example 1, suppose s of 0 equals 9. So where is it at 1 second? So this, remember that we started with the differential equation, right? So this is d of s that we started with. So when they're referring to s, they're referring to the antiderivative of our function. So this is, we'll note here, this is the position function. Because we started off with the ds dt, which represents the velocity, the s is going to give us the position. So it's asking us, where is it at 1 second? All right, so what we're going to have to do here is we're going to have to find the antiderivative of our velocity. So I'm going to do the antiderivative of our velocity function from 0 to 1, right? We start at 0, and then we go to 1 second. So that would be t squared minus 8 over t plus 1 squared dt. Okay, so the first part's easy. That would be t cubed over 3. Now this second part, we should represent any variables in the denominator as negative exponents. So it'd be 8t plus 1 to the negative 2. Right, so we're going to do the integral of that. So the integral of that would be negative 8, right? So that would be plus 8 to the t plus 1 to the negative 1. And we're doing that from 0 to 1. Okay, so if we plug in 1, then we get 1/3, and then 1 plus 1 is 2 to the negative 1, which is a half. Right, so plus 8 times 1 over 2. So 1/3 plus 4, 1/3 plus 4 minus, we're going to plug in 0. So 0 over 3 is 0. And then 0 plus 1 is 1. 8 over 1 is 8. So 4 minus 8 is negative 4. Plus 1/3 is, we should probably just do common denominators here. So 1/3 plus 12/3 minus 24/3 is negative 9/3. Did I do that correct? Oh, negative 11/3. Okay, so keep in mind though, we're not done yet here, because that just shows how far we traveled, or where our position is related to where we started. I mean, yeah, in relation to where it started. So what we're going to do is here, 9 minus 11/3 should give us our position. So that would be 27/3 minus 11/3, which is equal to 16/3. So our position is at 16/3. Okay, so again, remember that when we solve this, that just gives us how far we are in relation to the starting position. So if we want to find the actual position we're at, we have to add it to our initial position. Okay, so if I drew that graphically, maybe, yeah, we should have room here. So say we started here on our number line, right? So say this is 0. It doesn't matter where 0 is, but say we started here. What this value shows that we solve for is how much it changed, right? But how much it changed doesn't give us our actual position. So say we started at 1 and we traveled 2, right? So that 2 is not representative of the actual position. We have to add those 2 together to give us our actual position where we ended up with. Okay, part B is similar. And we already did our integral, so we don't have to do anything fancy there. We're just going to replace the 1 here with our 2. So we're going to do t cubed over 3 plus 8 parentheses. And maybe we should just do it as this because it's easier. 8 over t plus 1 from 0 to 2 this time. Okay, so when we plug in our 2 here, we get 8/3. And then plus, when we plug in 2 there, we get 8/3 again. And then we're going to subtract the 0. So 0 over 3 is 0. And then 8 over t plus 1 is 8. So this would be 16/3 minus 24/3, which is 8/3 negative. And remember again, this is just how far we've traveled from in relation to the initial position, so we have to add that to our 9. We should do 27 over 3 minus 8 over 3, which is 19/3 is our ending position. 19/3? Yeah. Okay, on to example 3. It says from examples 1 and 2, find the total distance traveled. So total distance traveled is a little bit different, right? When we just do the integral, it tells us where we ended up with, right? It takes into account if we're moving left, if we're moving right, and where we end up with. So when we're trying to find total distance, remember we're just doing the absolute value, right? So we're going to do the integral from 0 to 5 of this thing, absolute value t squared minus 8 over t plus 1 squared dt. And then let's just use our calculator to do this. So fn int. So you're going to do fn int 9, right? Which is math 9. To get to your fn int, you're going to fill out your information. Remember to get absolute value. Absolute value, you press math, you shift 1 to the right, and then that should be your first option to get our absolute value. And then, yeah, let's just calculate this. So, math 9 from 0 to 5, we're doing the absolute value, whoops, absolute value of x squared minus 8 divided by parentheses x plus 1 squared dx, and I come out with 42.59. Would be the total distance, the total units traveled from 0 to 5. Okay, and on to example 4. So it says a car is moving with initial velocity 5 miles per hour. Initial velocity 5 miles per hour, and accelerates at this formula, A of t equals 2.4 t. So it's saying how fast is it going at 8 seconds. So remember here, we're doing the integral of this. So 2.4 t dt. And it's saying that from 0 to 8, right? Because we start at 0 seconds, after 8 seconds is what we're looking for, right? And then we have to say plus 5. Right, because whatever this integral represents is just going to be how much it changed from its initial velocity, and its initial velocity would be at 5. Okay, so we're going to do our integral. The integral of 2.4 t is t squared divided by 2, so 2.4 t squared over 2 from 0 to 8, and then add our 5. Okay, so 2.4 divided by 2 is 1.2. So let's rewrite this. 1.2 t squared from 0 to 8 plus 5. Now, when we plug in our 8, 1.2 times 8 squared is going to give us 76.8. And when we plug in 0, that's just going to be 0, right? 0 squared times 1.2 is 0. So we're going to add our 5, and we get 81.8. 81.8, and that would be miles per hour. Miles per hour, which is super fast. Well, not more fast than you should probably be driving. Okay, so the second part is how far it traveled after 8 seconds. So we're going to stick with this, or actually stick with this version of our derivative, because that represents our velocity. And we know if we want to go from velocity to position, we're just going to take our 1.2 t squared and do the integral of that. So let's do, oh, and we have to take the absolute value of it, right? Because we're talking about total distance traveled. So 0, to 8, sorry. And then we're going to do the integral of that. Okay, so let's go ahead and do it. So the integral would be 1.2 t cubed over 3 from 0 to 8. We can even simplify that. 1.2 divided by 3 is 0.4 t cubed from 0 to 8. There's not going to be any problems with negatives, right? Absolute value. So we should be fine with the absolute value part. Now when we plug in here, we get 0.4 times 8 cubed, which is 204.8 minus, and then if we plug in 0 there, we get 0. So 204.8. Oh, I messed it up. Sorry. We forgot to add in the initial velocity here, which is not too big of a problem, but this should actually be plus 5 because there's actually 5 miles per hour added onto the velocity at that point. Okay, so this is still going to be the same thing. It's going to be 0.4 t cubed, but then we have our 5t here when we do our integral. And then we do that from 0 to 8. Okay, so when we plug in 8 here, we get 204.8 plus 40, which is 244.8. There we go, I missed that part. And when we plug in 0 here and here again, we get 0. So it traveled 244.8. And it's weird because the units is miles per hour times seconds. So really, we could do this. 244.8, and because it's miles per hour, we can convert the seconds to 1 hour over 3,600 seconds. And if we divide that, that should give us our miles. So 244.8 divided by 3600 is 0.68 miles. 0.68 miles. Or 0.068 miles. 0.068 miles. Which is equivalent to, if we want to find feet, right? There's going to be 5,280 feet per mile. So times 5,280 would be about 359.04 feet. Okay, so, I mean, if we get to that point, then our work is good. But if you want to figure out what that means in miles or feet, then you would just convert it. Okay, on to the last couple of examples, and these look complicated, but they're not, as long as you understand what we're looking at and how to interpret it from our graph. So it says the particle moves on the x-axis. The initial position x of I don't know what I put in there. Whatever this symbol is, I think it should be t. X of t is 15. The graph shows velocity, so that's very important. It's not showing us the position of our particle, it's showing us the velocity. And remember, when we're looking at the velocity graph, anything below the graph is moving to the left, which is negative. Anything above the graph is moving to the right, which is positive. So it's saying, what is the displacement between 0 and c? So displacement means where we end up at. Right? So it doesn't take into account the total area. It just says from where you started, where are you at the end? So then this is -4, -24, and +5. So if we add those up, -4 plus -24 is -28, plus 5 is -23. And we're just talking about the how much it changed, right? So it's 23 units to the left of where it started. So it says, what is the total distance traveled between 0 and C? So this part we're not going to take the negatives and positives into account, right? Total distance is the absolute value. So it's 4 plus 5, which is 9, plus 24, which is 33. And then it says, give us positions at A, B, and C. So this is not too bad, right? So what we know is that we started at 15. So from the starting point at 15 to A, it went -4. So it's going to be at 11, right? And then to get to B, it's going to be the -4 plus 5, which is 1. So it's going to be 1 to the right, which is at 16. And then C is going to be the whole thing added up. So it's going to be -4 plus 5 is 1, minus 24 is -23. So from 15, we're going to subtract 23, and that should be -8. Okay, and then A talks about acceleration. So the thing to remember about acceleration, because this is the velocity graph, acceleration is the derivative of velocity, and the derivative means the rate of change or the slope, right? So it's saying, where is the greatest positive slope on 0B? So between 0 and B, the greatest positive slope here would be at A. And between 0 and C, the greatest positive acceleration would be at C. Now keep in mind, there is also a pretty big acceleration there, but because it's not increasing, it's decreasing, we don't count B. Okay, and then on to the last one, and I just wanted to go over these because these are super handy as well. You may find them on your end of course exam. So it says the particle starts at x equals 2 when t equals 0. So it's giving us our initial position. Now it says A, find where the particle is at the end. So if we remember, if this is our velocity graph, right? So we're going to assume that these are graphs of velocity. If we find the area under the curve, then we can determine how far it's traveled, right? So each of these is 1 unit for our x-axis, and then it's 2 units high, and we cut it in half, right? It's a triangle, so it's half of that rectangle. So each of these is going to be 1 unit, 1 unit, 1 unit, 1 unit, 1 unit. So it went 4 units, right? So it started at 2, it went 4 units in the positive direction. So this is going to be, part A is 6. And part B, it says find the total distance traveled. So the total distance traveled here is 1, 2, 3, 4. 4 units. Okay, likewise for the second one, we're going to be doing the same thing. Each of these is 1 unit. So this is 1, this is 1, this is 1, this is 1. So notice in this case though, it did travel 4 total units, which is part B. But because it went to the right 1 unit, then went back to the left 1 unit, then went back to the right 1 unit, and went back to the left 1 unit, we ended up where we started. So that would be at 2. Okay, so really simple once you understand the concept of it. We're finding the areas underneath the curve, and we're using those areas to determine how far our particle has traveled and in what direction, and then the total distance by taking the absolute value, right, of our graph. Okay, that's it for today. Good job.